All right, I'm here today to talk about a small but emerging niche of construction at the intersection of concrete and robotics. My name is Jarett and I spend most of my time traveling to the most innovative construction projects in the world. And today I'm really excited to be here with you at FAU to talk about 3D printed concrete. This is an emerging technology that's very small right now, but it's growing at a very rapid pace. We'll look at some of the data on that in a minute. And today we're going to get into the reason why this technology is so important, the different types of robotics used for this process, the materials they use, the team you'll need to achieve a 3D printed home, along with some of the challenges that are facing the groups getting involved today. At the end, we'll also touch on the ways you can get involved. To start, it's important to remember that construction is the biggest industry in America. In 2022, it contributed $2.1 trillion of GDP, more than any other industry in the world, and yet it's been left out of the technological revolution. Everything from phones, cars, clothes are being produced with automation, and the biggest industry in America is not yet. This is a big problem, and a big part of it is that young people want to be like Elon Musk. They don't want to work with their hands, they want to work with their minds. They want to do something scalable. Just out of curiosity, by a show of hands, how many of you have ever done manual labor on a construction site? All right, and how many of you have ever written one line of code? It's almost equal, which is wild because we're at a concrete conference, and I'd expect it to be far more manual laborers, although we have a bunch of managers here, business owners. But this trend is getting bigger and bigger in terms of young people want to go into STEM fields, and if you have all of these brilliant engineers and nobody willing to work with their hands, there's really no other choice but to automate construction. So if you look at this chart, the number of people 55 plus on the job site has been increasing over the past decade, 2 decades. The number of people below 55 from both 16 to 24 and 25 to 54 has been decreasing. And so if you have not enough young people going into construction, it's really a matter of how are we going to have enough labor force to provide the needed housing. And everybody knows housing, the supply has been on a crunch, the prices have been raising. Really, automation seems to me the only solution. So let's reiterate the problem. We've got an aging construction labor force. We've got rising home prices, and construction is one of the most dangerous jobs in the country. After offshore fishing and logging, especially roofing, construction is a dangerous job. There's silica dust in the air and all kinds of challenges that ideally you probably wouldn't want your children exposed to. Young people want to work with robots and not their hands. They would rather hold an iPad than a hammer. So what can be done? We've got to automate construction. Now let's get into some of the different types of, or the data behind how fast this industry is growing. Back in 2017, the very first printed buildings were created in America. And this is actually put together by somebody in the audience, Kevin, the CFO of a local Florida company, Printed Farms, who operates a Cobod 3D printer. He collected this data mostly just from public information available on the internet, so the actual numbers are probably a little bit higher than this. But there's been an exponential growth curve in terms of the number of new printed buildings being constructed every single year. That's what really makes this so exciting. And I started covering this industry 4 years ago. I got to see from the very first printed buildings by Printed Farms, a garage here in Wellington, all the way to today where there's 100 home projects that we'll look at later. So what do? I travel around the world with the most cutting edge 3D printed construction projects. I share all of my primary sources. I film everything in person, and I post it all online at Automate Construction on whatever your favorite social media profile is. My real goal is to document the evolution of construction. I see a future where the whole process is automated, but it's going to take a lot of effort and a long time to get there. I'm trying to capture every single step. I also run the Automate Construction podcast, where I've hosted over 70 founders and CEOs of 3D printed construction companies and construction automation companies in hour-plus episodes that are all available online for free. So let's talk about the types of equipment they're using for automating construction, both on the job site and off the job site. This is the Icon printer. It's a gantry system on tracks, so it can run almost in infinite direction in the x-axis as long as you have a level job site. Of course, it's really difficult to level an infinite amount of ground, and if you did, it would probably be an unappealing row of houses anyway. It would all be flat. So typically, they'll just print one slab at a time, then move the printer to the next slab. This printer has a y-axis with the extruder head in the middle. Here's a video of their printer in action.
What are you pouring there?
This is a cementitious mortar. I'll get more into the ingredients in a minute. Here's an indoor example. This is actually the largest robotic arm in the world by Xtree in France, and they're printing out parametrically designed tables which were designed by clients on their website. So just by adjusting sliders, they can customize the texture, the curves, and the design, then click a button, and that file gets sent to the company, Xtree, where it gets printed out for a one-of-a-kind product that then gets delivered to the customer. And there's a lot of benefits to printing indoors. Unlike outside, you don't have to deal with environmental changes, changes in temperature, the rain. This specific company also has a misting setup so that you can retain humidity while the concrete is curing. This helps reduce the likelihood of cracking and reduces shrinkage. This is a group printing in Melbourne, Florida called Apis Core. They have a custom polar coordinate printer. It operates from a single base, which the printer rotates around. You're able to move this system to different locations to print, theoretically, an infinite print volume. They, for a long time, held the record for the biggest printed building in the world in Dubai. It was 8,000 square feet, a commercial building. Recently, that record was broken by Printed Farms. And you can see they've also got a custom mixer pump system. We'll talk more about the mixing process later. Here's the newest printer by Icon. They've got the Phoenix printer, which reaches 70 feet high, and it's operated off a boom system. Now, booms are notoriously unstable, especially at the tip when you're changing direction or acceleration. The way they compensate for this is with a laser-guided system that tracks its exact location within the print volume and adjusts while it's printing so that you get the nice smooth finish that you see. And here's a look at the finished product. This is just a pavilion. It's not going to be occupied, but you do get an idea for the scale that Icon's able to achieve with this system. And unlike the Apis Core printer, they didn't have to move it during the print, so there's no recalibration or readjustment. I did notice they use a lot of large sweeping turns in this print. That's probably because of the sway from the boom. So if you do a sharp corner, you might get wobble, which would be reflected in the layers. They do have sharp corners around the door frames, so this wasn't a fatal issue for the project, but they chose to do a lot of big sweeping round turns. It's really a unique structure. This is one of the tallest, I think the tallest printed building in America at 27 feet tall. You can get an eye for the bond beam poured around the entire roof. More of an experimental process. Typically it would be a flat roof, so pouring a bond beam on an angle is a big challenge. But the bond beam allows you to get a really secure connection to the roof, especially in hurricane regions like Florida. One of the main benefits of 3D printing is the parametric design that you could accomplish. So if you're trying to use formwork, a building with curves and angles like this would be really cost prohibitive. You need one-off formwork, which would probably never be used again. But with printing, a structure like this is maybe easier than a square with 90-degree angles. Here's a different type of construction automation using cinder blocks or CMU. This project is in Australia. They're adapting this to the American market, soon to be used with American cinder blocks. But it's similar to the Icon system in that it uses a laser-guided system to get pallets of cinder block loaded into the back of the truck, and then through an assembly line, it gets fed all the way to the final point, on the way receiving a spray of adhesive instead of mortar to bind each block to the next. It's up to you whether you want to call this 3D printing or not, but it's certainly its own form of construction automation, and they'll be setting up a factory to produce these in America pretty soon. Here's a really exciting printer by Diamond Age, and it's so fascinating to me because it's not just printing concrete. They've automated 27 different tools, including cutting, LiDAR, painting, and a pick-and-place system. So instead of just focusing on one aspect of construction, The printed walls or framing might only be 12% of the job. They're trying to tackle a lot more than that. They've got 3 different x-axes so that while one of the tools is working, people can detach and install another tool trying to maximize the uptime of the printer. This is in Phoenix, Arizona, where it gets above 105 degrees, so they've got a canopy over the top. This is nice for the people, but it's primarily because the sun beating down on the concrete changes the curing process. And so they have that set up with an operator booth in here, and we'll get more into their mixing process soon. One thing you should know is that even though it's called 3D printed concrete, this is more of a marketing term because 3D printed mortar just doesn't sound as good. It's not truly a concrete because the aggregate is all below 8 millimeters. This is partially because it needs to flow through a tiny hose. And when the concrete is flowing through that small hose, the large aggregate tends to push towards the center and create a plug flow zone. And the smaller mortar gets pushed to the outside. So with typical concrete, the larger aggregate leads to a stronger finished product. With 3D printing, after the phase and the hose separation, that's no longer the case. Let's talk about the material process. It's quite different from a typical concrete project where it gets delivered in a truck and poured into the formwork. Typically, they have a dry material, and this might be up to 40% cement, which is kind of a challenge, kind of cost prohibitive in many cases, because most concrete would be between 10 and 20% cement. This makes it more expensive, but some groups in Europe where they're not allowed to use concrete over 25% cement have found ways to augment this with fly ash or slag, some other ingredients that I'll show you in a minute. They either use a mixer pump or a batch plant mixer. The difference would be the batch plant mixer allows you to bring raw ingredients on site, just the cement, the sand, and the accelerants, so that you can customize the ratios depending on what the environmental conditions of the day are. The smaller mixer pump requires less manpower and less expertise, but you need to have a ready mix just add water solution where you have either super sacks or some kind of dry material delivery on site. You no longer have the control over the cement ratios and other details like that. From the mixer pump or batch plant mixer, it goes through a very long hose. It could be 90 yards for some of the larger gantry systems. And the hose is only 2 or 3 inches in diameter, so that pump needs to have a lot of power to push through the friction, especially at higher printing heights. A clogged hose is no fun. From the hose, it gets to the extruder head, which lays the concrete layer by layer with an adhesive between cold joints. So if you stop for printing for the day and you want to start the next day, typically for a large gantry system, they might print between 1 and 3 feet in a day. You can't have a cold joint because that'll create cracks. It'll prevent it from being a monolithic structure. So they'll use a dual bond silica or some other dual bond silicone or some other type of glue to bond the cold joint to the new fresh layers. Ideally, if you are printing continuously, you should get a monolithic structure because the concrete hasn't had time to set by the time the next layer comes around. So if you cut through it in a vertical segment, it should look very similar to how concrete would look in formwork. Finally, humidity management. Not every group will do this, but if you keep concrete, as you guys all probably know, if you keep it humid around the curing area, it cures much stronger. The longer the curing time, the less likelihood of cracking. Let's talk about some of the common materials used in 3D printed concrete mixes. Cement is the base, and unfortunately they use a lot more cement than most concrete products. Then they use sand, sometimes gravel, almost always below 8 millimeter aggregates with a few exceptions. With batch plant mixers, you can increase the aggregate size, maybe 4 millimeters. And then the next 5 ingredients are all cement reducing agents. So by including fly ash, slag, metakaolin, pozzolan, or graphene, you can potentially reduce the amount of cement you need in your mix. Some of these things don't have unlimited supply. Fly ash and slag specifically are byproducts of iron production and coal production. So right now, or previously, these things have been looked at as garbage, and then big companies like Lafarge bought up all the fly ash production, and now these ingredients are no longer cheap. They're becoming more expensive, and there's a limited amount of them. So if you want to print, let's say, a significant percentage of the homes in America, 5% or 10%, you're going to have to find some kind of solution besides the fly ash or the slag. So they've got things like metakaolin, pozzolan, graphene. Hopefully there's some material scientists that can figure out new solutions for printed concrete materials, because that's maybe one of the most important changes that could happen even overnight that could really make the industry much more cost effective. The printers work pretty well. They go where you tell them to, X, Y, Z coordinates. It's the material where a lot of the cost comes in and a lot of the challenges that people face. This is an example of the mixer pump system. So it would be fed in through the top. You have the dry mix fed in, and then you have a hose with water that gets adjusted with this system. And then it flows through the pump into the rotor stator, which is a metal tube with a rubber gasket inside and an auger that really grinds all the material up and makes sure it's a homogeneous flow when it goes into the hose. And this is where the hose would be connected. Back to the Icon printer, you see this is where their mixer pump system is. They have a silo up here which gets fed super sacks. So they will load up one of these giant concrete bags with a telehandler, put it in through the top of their mixer pump system, then it flows all the way through this hose into the printer, where it finally gets deposited into the print. Here's an example from Hive 3D, a Texas company, and I got to see this project almost from start to finish. The first two homes, they mixed the concrete by hand. You might call it the artisan method. They were loading by the shovel into an orange barrel and ratioing everything by how many shovel loads of sand, cement. It was an extremely arduous process, and it took them almost as much time to mix the concrete as to operate the printer. It's an expensive printer, so you want to maximize your uptime, your usability. They were able to do this by implementing this grout truck, which is almost like a batch plant mixer on site. They put the raw ingredients into the truck, and it gets fed into a mixing system rather than shoveling it in by hand. This allowed them to almost double their utility of their printing daily. So it went from printing a house in 6 or 7 days to being able to achieve these small, tiny homes in maybe 3 or 4 days. Now we've got one of the newer solutions, which is it's the only one in North America that I've seen using a ready mix truck. So the truck comes on site the way any other concrete truck would and gets fed into a mixer pump, which then goes into the hose. One of the big challenges here, typically these trucks show up on site, they dump their load, and they get out of there as quickly as possible so they can move on to the next job. But in this case, the truck needs to be there throughout the entire print day. So it's pretty expensive when you're preventing the truck from getting to its next site. However, it is the most readily available solution because any concrete supplier in the nation is able to deliver concrete like this. So it's an exciting change. We'll see how it develops. It's not all concrete. Some of the other materials being experimented with are adobe, geopolymer. I should note there are currently no adobe or geopolymer printed buildings permitted in America, but they do reduce the cement concentration, and lots of people are excited about them for different reasons. Here's an adobe print in Colorado by Emerging Objects, and you can see it's an interesting method. The big challenge is, can you convince people to live in an adobe home? Most people are used to a different level of finish. It does have good insulatory value, and there's some adobe homes in New Mexico that have been standing for hundreds of years, so the longevity is not the issue. But I don't know, would you guys want to live in this structure? Some marketing genius might be able to figure it out. Here's a geopolymer home printed in Nevada by Geopolymer International. And there's two different types of geopolymers. There's silica-based geopolymers and alkali-based geopolymers. Most people would require a polymer to have a polymer chain, and the silica-based polymers do have a polymer chain, whereas the alkali-based geopolymers are mostly just a lot of fly ash. The experts are divided on this, so you'll find people from both sides, brilliant academics who will argue till the sun goes down on which one qualifies as a geopolymer, but it's certainly an interesting realm for the future of 3D printing. Some people will try to tell you that the pyramids are geopolymer or the Roman concrete was geopolymer. It's very interesting, but I don't know enough about it. So let's talk about the duality of 3D printed concrete. It needs to be buildable enough that each layer can support itself without formwork. This is not common for concrete, so you're targeting zero slump. At the same time, you want it to flow through that tight hose up to 100 yards long. The way they sometimes achieve this is with a phase change. So to allow the concrete to flow through the hose and then also be stable and buildable for the print, they may add an accelerant at the extruder head or as close to the extruder head as possible, and this will rapidly change the concrete from that wet flowing state to a rapid setting state. We talked about this a little bit earlier. In the hose, there's a lubrication layer where the finer material gets pushed to the outside and the larger material gets pushed to the inside. This isn't great for the strength of the concrete, so many groups will agitate the concrete or mix it close to the extruder head. You might see a hopper with an auger, and this gets everything homogeneous before it's deposited. How do they structurally permit 3D printed buildings? This is an interesting topic because the permitting hasn't caught up to the technology yet. So at the moment, they're not dependent on the compressive strength of the printed walls at all. The printed walls need to be able to support themselves as a facade, but all the structural engineering is done with traditionally poured columns, usually using the printed concrete as formwork. So they'll drill a hole into the slab, print the wall, and then put rebar down in through the cavity of the wall and pour concrete in the top. And this will give them a vertical column like any other vertical column engineers are used to for them to do their structural calculations based on. Often you'll see a bond beam along the top perimeter of the wall connecting to the roof, especially in hurricane regions like Florida. Some cases they'll fill the entire wall. Obviously that's a huge amount of concrete that they're using and doesn't allow for much insulation. In those cases they usually have to insulate from the inside of the building and frame out the entire interior. Some groups have started using structural foam or aircrete for their 100% backfill, which can be serve dual purposes as both insulation and structural integrity. So here's an example of Icon's wall system. They've got horizontal rebar every 12 layers or so. Then they also have these rebar ties. It's not quite rebar, they're really just metal ties, thin metal ties between the inner and outer wall. For the longer stretches where there's no connecting piece like here, it helps keep the wall stable in its wet state. Then this cavity here is where they would insert the rebar at the end of the print and backfill with concrete, giving you the traditional column to do your calculations off of. Here's an example of a bond beam being poured. So they're actually using the printer in this case to feed traditional concrete into the top 1 foot of the building. And it has a continuous rebar cage all around the top, and this gives you a structure identical to what you would get with formwork, with the printed concrete acting as the formwork, but instead of removing it afterwards, it's a permanent formwork. You could also see a little bit of the insulation. For the area below the bond beam, there are columns every 6 feet or so with insulation filling the rest. Let's talk about the software behind printing a building. So it starts with an architectural design. Like any other building, you need to get a permit. So the permit process is very similar to traditional construction, but you can't print from that architectural design. So you'll need somebody to take that architectural design and make it into a 3D model. This might be an STL or a step file. Some groups will use parametric design so that you can customize the product with sliders, make adjustments to either the texture, the size. This allows you to create many different objects from one file without having to start from scratch every time. One of the many ways that this technology benefits from digitalization, parametric design is an exciting field that's been kind of underutilized in traditional construction because it's difficult to implement if you don't have a system that can just follow your design automatically. From the STL or the step file, it goes into a slicer, which is custom usually for each printer because every printer has its own parameters in terms of the radius it can accommodate or the speed it prints, the size of the nozzle head. Each group will typically have their own slicer, although there is one open source example called Slicer XL for slicing where you can customize those features. It's much better if you have one specifically built for your printer. From the slicer, you put in the STL or the step file and you get out the G-code file. The G-code is a map that the robot can follow, basically point-by-point instructions. Tells the printer when to start, tells the printer when to stop, and each point it needs to hit around for each layer. Some groups will skip the first 3 steps and just write the G-code file by hand. This is an arduous process, but it's achievable. It is expensive to develop a custom slicer, so groups that are bootstrapping oftentimes will write their G-code by hand, at least before they raise money. The standard print team, even though the goal is construction automation, it's still got a way to go before it's truly at click a button and press go. There's a lot of manual labor still required for achieving these projects. Most 3D printed construction sites will have, like any other construction site, a site supervisor. This person is responsible for looking at the construction plans, communicating with all the subcontractors, and generally managing site safety. Then you have the print operator. This is the guy holding the iPad who presses the go button and keeps in constant communication with the mixer pump operators because the print operator is the guy who sees the material coming out of the extruder head. And it's a lot of qualitative metrics like buildability, which they need to look out for. And if there's a change that needs to be made, they need to wait until all of the concrete gets through the hose in order to make that change. And the print operator might stop the print, and they'll be able to resume from the point they left off as long as the concrete hasn't had too much time to set. If there's an issue, the mixer pump operator will make that adjustment. If you're using a batch plant mixer, typically you have 2 people operating that system. One person might be loading the independent materials, sand, gravel, accelerants, while the other person is kind of clicking the buttons at an operator booth. From the mixer pump station, if you have a gantry system, typically you'll have a hose manager because the hose is so large, potentially like 300 feet long, it can hit the print, it can hit a person, and this is a 2 or 3 inch hose filled with concrete, so it's very heavy, very dangerous. It can knock over a wall or knock someone out. I call it the hose hugger because on a large gantry system, they'll be hugging the hose through the whole print, trying to make sure that it doesn't run into anything. You also have a reinforcement placer. This is the person responsible for placing the horizontal rebar and the ties like we saw in the last print. Another thing you can do is place outlets in the wet concrete. Because the concrete is still wet, it's malleable, it's like Play-Doh almost. You can install some of the systems, even PVC pipes for where you want electrical pass-throughs. It's one of the efficiencies that if a group is planning in advance, they can get a lot out of the process just in the printing phase. If you have a robotic arm system, the hose runs up through the middle and doesn't really require the hose management. That could be a big step to improve the automation of the gantry systems if someone came up with a clever hose management system. Now some of the challenges. It's a new industry, and that comes with all kinds of troubles. The equipment, in terms of you have stepper motors like a typical printer, you also have the mixer pump, the generators. Pretty much anything that can go wrong will go wrong. The cement concentration being so high is another big challenge, especially if you're trying to hit specific CO2 goals. Another one is the raw material longevity. If a stepper motor breaks and you have your printer material sitting around for a few weeks, especially in humid places like Florida, your material can go bad. And it's expensive, so that's a big cost if your material's not stored correctly. Some places like Canada, it's so dry they can leave the material for a year or 2, but especially in Florida, keeping your material stored properly is a huge part of achieving a cost-effective project. Permitting, like we discussed earlier, is underdeveloped for 3D printed concrete. There are groups like ACI, ASTM, who are trying to develop permitting standards right now. One of their goals is to keep this open-ended so that people can continue to innovate and not get stuck in the current status quo. Hopefully that formwork or the guidance from the permitting will make it easier for more projects to be achieved. But at the moment, they're having to conform to existing standards. Another big challenge is that marketing myths lead to poor expectation management. Some of the most viral videos about 3D printed houses have been about $10,000 3D printed house or house printed in 24 hours. None of these things are true. And when people see these things and then try to buy a printer, they become tremendously disappointed when their first project doesn't go how they expected. So it's the groups that go into it expecting the challenges of being on the cutting edge, the bleeding edge, who tend to be successful in printing a second home or third home after they get started. A lot of people look at the Tesla factory in Fremont and use it as an example of what happens when you use too many robots, and they had to then pull back the robots and put more people on the job site. But when I look at the case study of the Fremont factory Tesla took over from Toyota, I see a different story. They needed to add as many robots as they could, doing things no car manufacturer had done before, to figure out what robots worked and which didn't. After they tried everything, they rolled it back and brought more people onto the job site. From there, they've achieved a lower human to robot ratio than any other facility in North America, and it's also the most productive facility per square foot in North America. So from Toyota's failed factory, they were able to implement first too many robots and then just enough. So what I see from this is that sometimes you need to start with too many robots in order to find the Goldilocks number. And from there, they were able to further automate the Tesla facility in Texas, where they're using now gigapresses. I think this will also be true in 3D printed construction. It will be the companies that implement a lot of robots, which some of them won't work at first, who learn the lessons to scale it up and ultimately use as many of the good robots as they can. Let's look at some of the notable projects completed by 3D printed construction companies. Here's a 24-home project by Diamond Age in Casa Grande, Arizona. They've got 4 printers on site, and many of these homes are already moved into. When they're completed, they look identical to local homes in Casa Grande, built with Adobe, and it's here's a drone flyover. You'll notice down here, there's one missing. And I think this is probably because it didn't line up to the Diamond Age standard. So maybe they had cracks in the process. Perhaps their material parameters weren't right. But they almost certainly intended to have something there. Here's the Icon project, which is 100 homes in Georgetown, Texas. This is the early stages where some of the homes have completed printing, some are getting now. Some of these have been moved into, but you can see they've got 1, 2, 3, 4, 5, 6, at least 6 printers, each with their own mixing plant. This is, to date, the biggest project in terms of the number of units in the world. Here's the biggest printed house in America in Houston, Texas, by Perry. And they achieved this project by first printing the back half, then moving 2 of the vertical axes to the front to accommodate the full size of the print. And they've got a silo there where they're loading the dry mix, and it gets fed all the way through the hose into the extruder head. You can see the print operator watching the layers, making sure the quality is good. And this home is going to be a total of 40 feet high. The printer itself only went to 20 feet, but they prefabricated parts of the chimney, which then get lifted into place and put on top to reach that 40-foot height. Here's a project at SpaceX by Icon, and it's at the Ad Astra School, so it's where Elon Musk will be sending his kids to school. And I believe it's a $3 million project, totally unique, large circular design, which would be very expensive to do with any other type of construction method. Floor-to-ceiling windows right on the beach. Really a beautiful project. It's still under construction in this picture. This is a project, now the biggest printed building in the world, completed by Diamond Age. They had to move the printer 5 times. So first the printer was here, Then now they're printing the second section here. The printer will then be moved to the third section, the fourth section, and the fifth section. And you can see the finished product is a 10,000 square foot equestrian facility. So Printed Farm started with just a small garage in Wellington where they didn't need any permits for an agricultural building. From there, they scaled up. They did a home with Precision Builders in Tallahassee, then moved on to this enormous building. Even though it's just a horse facility, they finished it up to a really high standard with all kinds of automation systems, including chemicals to keep the bugs away, enormous laundry facilities, and there's 3 printed buildings on site. They've got a rotunda, which was printed circular, much easier to print things that are circles than use traditional construction. They've also got a printed manure shed in the corner up there. Here are the references from some of the stats and data that I had in the presentation. And if you'd like to get involved in 3D printed construction, there's a bunch of different ways you can do that. You might be an architect or a designer, and in that case you could do 3D modeling or CAD work, parametric design. If you're an engineer, maybe you can figure out a solution to that pesky hose management. Or you could further automate the mixing systems, create additional tooling like Diamond Age, other uses for the gantry system like cutting, placing, scanning. There's also tons of room for innovation in architecture and civil engineering. It's like an iceberg where only a tiny bit has been exposed so far, and a lot of it's a mystery. So if engineers are able to create structures that are dependent more on compressive strength than tensile strength, perhaps the natural advantages of concrete could be dependent on more for the structural integrity of the building. And that might depend on permitting from ASTM or ACI to be achieved, but that's a huge area for development. Then if you're a software person, you can develop slicers, custom slicers for companies, or there's certainly room in the market for a slicer that would be able to work with a variety of printers. New design tools would also be fantastic. Imagine an AI software where you could say, I'd like a 2-bedroom home with this many square feet, this kind of kitchen in this style, and from there, it just spits out like ChatGPT, a printable G-code file. There's no question something like this is going to exist within the next 5 to 10 years. It's just a question of who's going to make it. Material science, like we discussed, reducing the need for cement without limited materials like fly ash and slag. If some materials genius comes up with a solution to use, say, 10% cement in the mix, where your cost for the concrete would be on parity with traditional concrete, that would really unlock a tremendous cost advantage overnight. Finally, real estate development. If you buy a printer, you could produce houses and operate either as a GC, hiring the printer as a subcontractor, or operating the printer yourself. Ultimately, that's who's going to be doing the buildings. But they depend on all these other people to achieve it. That's the conclusion of my presentation. And if you have any questions, I'd love to take them. Thank you.
Financially, if you bought a piece of land, let's say in Florida, where most houses now are required to be built out of concrete single wall, what would be the difference between the cost of construction, the way most people are doing it now, and the cost of doing it with a 3D printer? A 2,000 square foot home, for example.
The quick answer is 20 to 40% more expensive than traditional construction. The caveat is that every region has tremendously different construction costs. And so in one town, the framing might cost double another town, and so it's very difficult to give a one-size-fits-all answer to this. You have some groups like Icon claiming that they're now printing at $34 per square foot for just the wall structure, which includes the reinforcement and the insulation. There may be some hidden costs like the transportation of the printer or the increased needs for foundation. Because it's such a heavy building and the printer itself is heavy, they may need double the foundation as a typical building. So there's a lot of cost associated with printing a building that may not be present in traditional construction, not directly reflected in the cost of the wall. Right now, I would love to see a project come in cheaper than traditional construction. Nobody's shown me a finished project cost analysis that seems cheaper than stick-built or cinder block construction. But this technology is advancing much faster than the traditional types of construction. This is brand new. You saw the number of printed homes is increasing. So as more people get involved, they're constantly figuring out ways to improve by 1%, 5%, 10%. So the trajectory of automation is very promising, especially when the cost of labor is increasing so quickly and the skilled labor force is in such short supply. At some point, even if everything stays the same, labor could get so expensive that printing concrete becomes more cost effective anyway, with no further advancement.
In Arizona and Texas, any idea of the market reception and if people are buying these homes faster or they're sitting around, they have to be kind of coaxed into buying them? Or?
Yeah, in Casa Grande, they sold at a very attractive price point, like $260,000, which is very competitive for the region, so they filled up pretty quickly. That was a project with Century Homes. And I talked to one of the people who lived in them when I visited with their CTO. I try not to knock on the doors of too many 3D printed homeowners, but the one they introduced me to seemed thrilled about it. They can't really tell the home was printed in that case, so the people they sell it to might not even know. And in that case, the reception is easy, as opposed to some of the homes have exposed layers, and it's totally obvious to anyone that walks by that it's a printed home. There's an example of that I visited by Habitat in Arizona as well, built with a Cobod printer. And the guy Marcus, I filmed a tour through his home on my YouTube channel, and he loved it. He was really excited about it. You could tell, huge grin on his face. I'm sure every person that walks in, he tells about how much he loves living in a printed home. But it's a matter of taste. Some people like being a part of the tech revolution, like early adopters. It's definitely in that early adopter stage where some people love it, some people hate it. Any other questions?
The water cement ratio, the mix looks like, it's a flowing concrete. What about the durability of these products after it hardens? That's the first question. The second one is, if there is too much of conditional reinforcement, how does the automation will be able to handle that?
Most of the reinforcement is within the cavities of the wall, so it's difficult to tie vertical and horizontal rebar within the printed wall itself. By placing those things in the cavities and pouring concrete in afterwards, they're able to accommodate a full rebar cage with traditionally poured concrete. And the beauty of that is then the structural dependency on the printed wall is very low. So even if it does have an aesthetic crack, that's not a structural challenge for the building. It will stand. Generally, it's hard to say long-term durability because these buildings are so new. The ones printed in the past few years are still standing. They look good. But in my opinion, we'll have to wait 30 years to see if they really last 30 years or not. Some people will say you could do lab testing to simulate freeze-thaw cycles, but I'd really like to see it in person before I tell you it's going to last 30 years or 75 years. We'll see.
The permeability is one important parameter when you look at the durability.
Permeability?
Yes, of the hardened concrete,
Yeah, it has very low permeability, and some projects we're not anticipating them to be so airtight. And actually, the project I stayed at, Icon's East 17th Street Homes, somebody there had a CO2 detector. And just with 4 of us having some pizza in the building, the CO2 levels were rising in a 2-bedroom, 2-story home, 2,200 square feet. From that project, Icon realized they needed to increase the ventilation in the building because it was so airtight, which is generally a good thing for construction. You want your building to be airtight for environmental, reduces the demand of the HVAC system. Do you agree, permeability, you want to keep that low?
Well, usually permeability is associated with the durability, so that's the reason. And if it's a flowing concrete, obviously the water cement ratio is high, and we are using mainly fines, very fine particles of sand.
That's right. There was someone behind you with a question, sorry.
So first of all, very interesting presentation. Thank you for sharing. But my question is actually directly towards you. What is your background and how did you find yourself in such a niche field?
I studied business and engineering in college, and from there saw one of those $10,000 3D printed house videos, which got me really interested, but I had done some construction work in the past, so I knew off the rip, that wasn't ever going to happen. You can't even do electrical in a roof for $10,000, so you're not going to print a whole building for $10,000. That said, it got me excited enough about it to contact Winsun in China, and I visited they had a $200 million facility in 2019, bought my first camera, filmed the facility at Winsun, posted a couple videos on the internet, and they did better than I expected. So then I continued traveling around to as many printed buildings as I could, posting more videos, and it kind of snowballed into a place where I've traveled, I think, to more printed buildings than anyone else in the world, and interviewed as many founders as anybody, trying to learn as much as I can about how automation progresses on the construction site.
What's the time to mobilize one of those linear printers?
Great question. That's a big challenge for the gantry-style printers. It can be 2 or 3 days to set up the printer. You might be assembling it one day, calibration the next day, and then on the third day you might be printing. It's almost a construction project in and of itself. They might be resting on 2-ton or 4-ton blocks, depending on the height of the structure, and you really need to get it very fine-tuned, because if it's not square and plumb, your building won't be either. So that's a big benefit to the smaller robotic arm systems, which might only take a couple hours to get set up after you roll them off the trailer. Then disassembling the systems another day or two, depending on the size.
Any other questions?
Do you have a sense of if these big public home builders are going to move from single developments to, quadrupling or 10xing next year or 2 years from now?
Yeah, that's another great question. Icon was really excited about scale, and they said there's going to be economies of scale and it'll make everything more cost effective. So once they finish up this project with Lennar, the first project really at scale, I think that question will be answered when either Lennar does another one that's bigger, or if they don't, maybe they didn't necessarily reach those economies of scale yet, and then Icon will have to go back to the drawing boards, redevelop a system. And as we see they are developing the Phoenix printer, that may already be the case. So they may have tried it, it was still more expensive, and now they're trying to figure out a solution that's going to be even better. And that's the way technology works. It's tough in the beginning. Like LED lights were really expensive when they first came out. Flat screen TVs were super expensive when they first came out. But as people continue to iterate and improve upon them, things get cheaper and cheaper.
Is this type of construction better for the environment?
It's hard to say. The cement concentration makes it seem like it's not, because cement is the big CO2 producer in concrete. And so if you have a higher cement concentration, you're probably going to release more CO2. But instead of formwork, where you need a full 100% fill, with 3D printing, you might be able to reduce that by 25% or 30% and use less concrete, because you don't need the entire interior of the formwork to be filled out. So depending on how you design it, some people argue. There's actually an MIT study that Icon did recently, which claims that printed buildings for a lifetime analysis of 75 years have between 2 to 6% reduction in CO2 compared to a traditional stick-built project. And so that's a brand new study by MIT, a white paper. So maybe yes. Maybe it's more environmentally friendly. Depends if you believe MIT or not.
Also build interior walls.
You can print the interior walls. If you're doing a 100% backfill, then you'll need to frame out the inside so that you can have insulation along the entire continuous insulation on the inside. But if you're not backfilling the entire wall, then you can have insulation within the inner and outer layer of the wall itself. And in that case, you can leave the printed wall exposed on the interior, which helps reduce the cost if you like the finish of the printed layers. Last question.
So has fiber reinforced concrete been used in this?
Yeah, they do use some fiber reinforced concrete. They've tried the metal fibers. They've tried polypropylene fiber. It's challenging because it makes it more sticky in the hose. And so the more fibers you use, the higher likelihood of a clogging event in the hose, which is horrible. If it clogs, they'll have to bring out sledgehammers or flush out the hose, or maybe the hose is just garbage. So they generally don't use fibers in the mix. Thank you all very much. Those were great questions, and I was really happy to be here at FAU with you today.
So next thing that
that we have in the agenda is break, 15 minutes break. So you're gonna go to the exhibit hall, then come back at 2:45. We're gonna have our last presentation by our own Professor Lou, Dr. Lou. She's gonna talk about recycling concrete waste. It's gonna be an interesting presentation, followed by networking.